Now, why is this significant? Well, one of the questions that we often get asked is predict, or what would happen, which one would have a higher melting point, which would be the stronger ionic compound, etc., etc. And oftentimes when we're playing this game, what we want to do is we want to keep in mind those idea of size of ions and differential in charges. Now, when we play this game, please remember, we're painting with a very broad brush here. So there's going to be a ton of exceptions depending on what's going on. Typically, when I play this game with my students, I want to make sure that I keep as many things as similar as possible. So I want to compare like a +2 to a -2 in all the variations. Because even though you might sit there and say like, well, what happens if I had like a +3 and a -1 and you're like the differential's the same? Yes, but then other things are in play because the geometries can change and et cetera, et cetera, et cetera. Without going into a whole long litany, let's try to keep things similar. So let's take a look and let's play the game for each of these pairs who has the higher melting point. And so what we're going to do is we're going to start off first with CaO and MgO. Both of these are +2, -2, right? So Ca2 plus, O2 minus, Mg2 plus, O2 minus. So the differential in charge is the same. In other words, one is as positive as the other one is negative, right? And so the overall change in charge is about 4, right? So +2 to -2, so it's an absolute value of 4. Now, that alone, I can tell that these guys are going to be attracted to one another and very attracted, but I believe that in this case, the MgO is going to have the higher melting point because magnesium is higher up on my table. When I look at my periodic table, magnesium is in the 3rd row as opposed to calcium that's in the 4th. So what that means is that magnesium will be the smaller ion, and because it's the smaller ion, that means that it will be closer and therefore exert a stronger magnetic force or a stronger magnetic field. Whereas the calcium, just as positive, just as negative, but because it's bigger, they're now further apart, and so the magnetic field is slightly weaker. So in the case of CaO and MgO, our winner is going to be the magnesium oxide. This is going to be the one with the higher melting point. So, okay, do the similar trick. Now in the second scenario, what I'm doing is instead of playing with the cation, I'm going to change the size of the anion. Now, again, in both of these, we're looking at, in essence, a metal that is going to be surrounded by some nonmetals, right? So the metals in the middle, the nonmetals are surrounding it in some variation, which is fine. But what I find here is that I'm comparing magnesium chloride to magnesium iodide, and I know that the iodide ions are going to be much bigger than if we were doing something like the chlorines. So maybe with the chlorines, I might see something that looks more like this, okay? So for example, this would be my MgCl2, and this would be my MgI2. Okay, and again, just rough idea, but so you get the sense of it. Now again, the differential is the same, +2, -1. So the absolute value is about 3 here between the two of them. But because the magnesium iodide is the larger one, I think it's going to therefore have the weaker attraction. And as a result, we find that the MgCl2 has the higher melting point. Or the MgCl2 is the ionic solid that is more tightly held together. Okay? Tomato, tomato. Now, for the last example, I'm throwing a bit of a curveball. And here's why I'm throwing the curveball. Because if you asked me who has the higher melting point between the calcium oxide and the aluminum phosphide, I would want to pick this guy. And the reason I kind of want to pick him is because here you're looking at +3 and -3. So the differential here is roughly 6, as opposed to here it's going to be +2 and -2. But fun fact, if I actually look up the melting points, I find that the calcium oxide will melt at a slightly higher point than the aluminum phosphide. Huh. Fascinating. Why is that? Why would the calcium oxide, even though it doesn't have as much of a differential, why would it have the higher melting point? And the answer is we have to look here at the oxygen anion. Because what the oxygen anion is doing is that this is an element, or an ion in this case, that is in the second row, as opposed to phosphorus that is in the third. And what we find is there is a huge change in size from the second to the third energy level. And since we have this large change in size from the second to the third, what that means is that although the coulombic differential is less in calcium oxide, the proximity between the two ions is a bigger deal. So, this is not a fair question to ask a typical student if the only thing I do is I sit there and I say who has the higher melting point. Because just off of that, my gut would be to go after coulombic differentials. Instead, the way I might phrase this question is we find calcium oxide to have a greater melting point than aluminum phosphide. Explain why. And so then in my explanation, I would speak into, well, even though calcium oxide is +2, -2, and the other one's +3, -3, the size of calcium oxide is smaller than the aluminum phosphide. And as a result, that proximity is now going to be the more important factor in determining how tightly those ions attract one another. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.